All right, we're just going to sit around for the next 10 minutes or so and just chat about these logarithmic functions and exponential functions and their graphs and some of the features of them and asymptotes and all kinds of weird and wonderful things. There's no real sort of goal, I guess, other than to just try and get to understand a little bit more about what the graphs are, how they get transformed when we change values. So yeah, just sit back, relax and enjoy the journey, and we're going to do some deep thinking on this. Hopefully it will help make sense. First of all, we've got two functions here. I've got my exponential, y equals 3 to the x, and the logarithmic function, which is the equivalent, is y equals log to the base 3 of x. I've also thrown on here my linear y equals x, because remember in a previous video we talked about the fact that they're inverse functions. So what were two of the features that we can identify that make them inverse functions or opposites of each other? Well, the first one is this reflection along the line y equals x. The exponential and the equivalent logarithmic function are reflected along the line y equals x. So we'd say that one feature that shows their inverse is that they're reflected along that line. The second one has to do with coordinates. So if I pick the coordinate on, let's say, my logarithmic function, the coordinate 3, 1, and I reverse those digits to 1, 3, I would see that the coordinate 1, 3 would sit actually on my exponential. So the second feature that shows their inverseness is that if you reverse the coordinates on one, that point will be on the other. So if I took the point 0, 1 right here on my exponential, reversed it to 1, 0, I can see that 1, 0 is on my logarithmic function. So that's one interesting feature of the relationship between these two. Find the equations of any asymptotes. Now, an asymptote is a line that represents something where the function gets really close to it, but never ever touches it, or never crosses it or touches it. So let's have a look. My exponential function, I can see as it comes down here, as my x values get really small, they get closer and closer to the axis, to the y equals 0, but they never ever get there, and we're going to talk about that in a minute and show why that is the case. So there's an asymptote there, and the horizontal line that goes through the y value of 0, cuts the y-axis at 0, has the equation y equals 0. For my logarithmic function, I can see as these y values get very far down in the negative, but they never touch the y-axis. So I've got an asymptote here as well. And it's a vertical line going through the x value of 0, so it has an equation x equals 0. They're the equations of the two asymptotes for these two functions. All right, so far so good. Let's get a little bit weird for a second. Hang on tight, there's going to be a few ideas in here we're going to explore. Discuss any limitations on the input or the output for each function. So is there certain things you can or can't put in for your x values, or there are certain things that you just won't get out for your y values? Now, here's something I want to share with you. This works for me. Hopefully it'll work for you. When we're trying to think about what functions do, I like to think of this little model here, where it says, look, what happens to the function when x equals 0? That'll give me a point that I can consider. But then what happens as my x values move towards massively big numbers? What happens to my function? As it comes back towards 0, so I get positives, but tiny positives, like fractions, thousandths of a fraction. What happens to my function? And then the same in the negative direction. Let's take that idea and apply it to my exponential. As my x values get massively big, what happens to the y values? So if I had 3 to the power of a million, I'm going to still have a positive y value that's going to be massive. 3 to the power of a million is going to be a massive number. So I can go with massive x values, I'm going to get a massive y value. What happens when I come back though towards 0? So just over 0. So let's say 1,000th. If my value for x was 1,000th, what happens to my y value? Well, if you put this in your calculator, you're going to see that this is just over 1. And we can see that on our graph. If x value was like 1,000th, it's just a tiny bit above the axis here, my y value is just over 1. So that actually lines up with my curve. Now what happens if we go the other way? What happens if I go just the other side of 0 into the negatives? So a negative 1,000th. Well, if I put that in my calculator, I'll see that it's just under 1. So my function sort of continues across the axis here. In fact, if I put x equals 0, I'm going to get a y value of 1, because anything to the power of 0 equals 1. Now here's where it gets interesting. We talked about this asymptote before, never getting to 0. Let's have a look at why. What happens to my y value when my x values get massively negative? Let's take 3 to the power of negative 100,000. A negative index means 1 over, so I've basically got 1 over 3 to the power of 1,000th. That's going to be a tiny number. Now this is my y value, because I've got a massively negative x value, my y value, but you'll notice it's still positive. Okay, 1 over some big massive number is a positive fraction. It's tiny, but it's still positive. So even if I had 3 to the power of negative a billion, if my x value is negative a billion, my y value is still going to be above 0. It'd be 1 over 3 to the power of a billion, a tiny, tiny fraction. But you can see it never actually gets to 0. So the bigger, no matter how big the number gets on the bottom of this fraction, it's always going to be slightly above 0, which is why it's an asymptote, why it never gets there. So that mental exercise, I guess, of thinking what happens when x equals 0, what happens when x is massively big, what happens when it's massively negative, what happens when it's just either side of 0, really helps give you a picture of what your function does. Whew, I hope you guys followed that. Like it's actually, as you get further into maths, it's actually a really good technique and something to do. We are now going to discuss, based on that, what are some of the limitations for our input. Now, are there any values of x that we can't put in? Well, for our exponential, no. There are no limitations. I just saw I could put in massively big x's or massively negative x's, and I'm always going to get a y value. So there's no restrictions on that. But for my logarithmic function, I've got an asymptote that comes down here, which means I can never, for this logarithmic function, log base 3 of x, I can only put in positive x values. There are, like, these negatives, it just doesn't exist. I can't have a negative log. So my x value has to be greater than 0 for this logarithmic function. So there is a restriction on the input. I can't put x values in here. These negative x values don't fit in. They won't work for this logarithmic function because I can't have a negative log. What about the output? All right, so let's have a look at my exponential function. Well, we just discussed this whole idea of this line getting close but never touching y equals 0 or never going into the negatives. So there is a limit on the output. It will always be a positive value for y, no matter what x value I put in, because on this side, they're always going to be massively big, and this side, they're going to be massively small, but they never get into the negatives. So for this exponential function, the limitation on the output is that y will always be greater than 0. Is there any limitation on the output for my logarithmic function? Well, no. I can, my y values can go up as high as they want to, as I go for massively big x values. And as I come down towards 0, my y's will go, my y's will just continue to go down. So there's no real limitations on the output. It was only a limitation on the input. But for the things that I can put in, there's no limitations on the output. All right, there was a lot going on there. So if you need to pause, go back and have a rewind. But we talked some really deep ideas there. And hopefully that just helped you understand a little bit about how we could go about proving or trying to describe what functions are doing. All right, let's move on and have a look at what happens when we do some transformations on logarithmic functions. So I've got my log here, log base 3 of x. And this is how it graphs on this blue line here. If I change this and have log base 3 of x plus 2, so my logarithmic value here in brackets is x plus 2, it transforms my function horizontally to the left. So I'm adding 2 here because remember we had an asymptote. So for this one here, we had this asymptote at x equals 0, this vertical line here. Well, by doing this, my asymptote will happen when this equals or gets close to 0. So my x, as I get close to -2, okay, so sorry if that didn't make sense. Here, as my asymptote happened as x got closer to 0. Okay, so as this value became closer to 0, that's where my asymptote was. And you'll see that's the same up here. As my x value gets close to -2, this is where the asymptote is, because effectively that bit is now getting close to 0. And remember, we said we can't have a negative logarithmic in there. So that's why it moves along, and I can look at that and go, oh yeah, the asymptote is going to be at -2, because that's the point where this bit gets close to 0. And the reverse happens going the other way. If I have log to the base 3 of x minus 2, so I've got a negative in here, then my asymptote now will be at the point where x equals 2. And here it is. There's my asymptote. Okay, because in the bit in the brackets will be 0 when x equals 2, and that represents the limit of where my logarithmic function will not ever cross that point into the negatives, which we said we can't have a negative log. So out of all that, the transformations are, and we'll do an example in a minute, okay? If I add to the x value, my function shifts to the left, as does the asymptote, and it moves that far. If I have a subtraction from the x, my function graph shifts to the right, and the new asymptote moves with it accordingly. What about instead of, so this is the one we just finished up with, this log to the base 3 of x minus 2. If I add a constant, well, just like parabolas, all it does is it moves the graph up or down. So if I had log to the base 3 of x minus 2 plus 3, it's taken that same curve that we started with and just shifted it up 3 places. So I can see here it cut the axis, or the y equals 0 value at 3, and it's moved up 1, 2, 3 places. I've just shifted it up 3. Or vice versa. If I've shifted down 3, it's come down from here. 1, 2, 3 places. Okay, so adding a constant simply moves it up or down. So here's the kind of question you might get, and we're going to go through and answer some of the questions that relate to this, this particular logarithmic function. Y equals log to the base 2 of x minus 3 plus 1. All right, are there any transformations, and how do we describe them? Well, yes, there are. I can look at it and I can see, well, I know that because of this bit in the brackets, x minus 3, that it is shifted to the right, and my new asymptote will be at the value x equals 3, which I can see it does here. So that means the x minus 3 part in the brackets means the curve has moved 3 places to the right. That's a statement you could make if you were asked to describe any of the transformations. The constant, the plus 1, means that the whole thing gets moved up 1 place on the y-axis. There's an answer. Describe the transformations. We've done it. We've described it based on those 2 sections of the logarithmic function. Are there any asymptotes? Well, there is. We know that the asymptote will happen where the section in the brackets here is 0. So that's going to be when x equals 3. And I can visually see that on my graph, that the asymptote occurs at this x equals 3 value, because the value of 3 will make this 0. I can't go into the negatives, so that's where my asymptote will occur, at the line x equals 3. Are there any limitations on the input or the output? All right, well, let's have a look. We know that this can't get into the negative. So there is going to be a limitation. I can't put an x value in there that would make that negative. So my x minus 3 bit has to be greater than 0. So I'm just going to move that -3 across to the other side, change sides, change sign. So the limitations will be my x values have to be greater than 3. Finally, where does it cut the axes, if anywhere? So we're going to go through and prove this. Now I can look at that and visually it looks like 3.5, but I don't know. Is it 3.55? Is it 3.50001? I don't know. We're going to prove that I think it's 3.5. Let's go ahead and prove it. So here's how we do it. We know that the x-intercept occurs when y equals 0. So we're going to set my y value here as 0. So my log function now looks like this. Log to the base 2 of x minus 3 plus 1 equals 0, because that will be where the x-intercept is. Now, if I can get a value out of this, then I've found it. So I'm going to rearrange this. I'm going to take my plus 1 to the other side, okay, because now I've got this in the form that we looked at in the previous video, where I've got a base, I've got the index on the other side, and I've got my value here. So let's rearrange that and write it in index form. 2 was my base, so 2 becomes my base. -1 is my index, so it's my index, equals my value. Now I can try and solve this. Now I know that 2 to the -1 is a half. On the right hand side I've got x minus 3. Oh, now you can see we're somewhere where we can just solve this, can't we? Bring the -3 across, it becomes a positive 3. So my x value is in fact 3.5. So this, for this to be true, my x value has to be 3.5. That's where it cuts the x-axis. All right, what about the y-axis? I don't think it does. Have a look. I mean, just visually, I've got this asymptote, so it won't. But let's prove it. The y-axis will be where the y-intercept will happen when x equals 0, doesn't it? When the x value is 0, that's where we cut the y-axis. So let's put 0 in where my x is. So now I've got y equals log to the base 2 of 0 minus 3, which is -3. And here's where it all falls apart, because we've just said a number of times through this video, we cannot have a negative value in my log. So, nope, it won't work. There is no y-intercept. Man, we covered a lot of territory in that video, and there was a lot in it. So I hope you followed. And yeah, like I said, feel free, rewind, go back, have a look at any of the things. We talked about transformations, we talked about asymptotes, limitations on the input or the output, and whether or not it cuts the axis. Good job, guys. Well done.